Okay, so let's solve the exercises, and I should warn you in advance that those exercises start easy and then they become more and more hairy. Okay, so let's start from the easy one. We have a finite language over 0, 1 star. Does it mean that L1 is a set only with a finite number of strings? And the answer, of course, is true. That's what it means to be finite. It means that it's a finite set. To remind you, a language is just a fancy word to say set. So if I say a finite language, I just say a finite set, which means that it has a finite number of elements, which has a finite number of strings. Okay, next one. Let's look on L2, which is all the strings made out of only zeros, such that they are 0 to the I, where I goes over all the integer numbers. So think about the language which is just 0. This is, of course, a regular language by definition. And then you can just take L star. Right? This is just the clean star of this language, which by definition is a regular language. So this language is regular. Okay, next one. This is the language of all string of 0 to the 2i. So the same trick works, right? Take the language that contains only the string 0. We know it's regular. Concatenate it with itself, right? And then take it clean star, right? What you will get here is the language that has strings made out only of zeros that their length is 2 to the I. Okay. What about all the strings of lengths made out of zeros that are their length is 17 to the I, namely all strings that their length is divisible by 17? Well, same thing works, right? Concatenate the language that contains only 0 with itself 17 times, right? In fact, any language containing only a finite number of strings is regular. So, as we saw, so we do it 17 times. And now we just take the clean star, right, on this. And that would generate, it's a clean star over the language which contains only one string, which is 0 repeated 17 times. And you take a clean star, you will get all the strings that have 17, that their length is divisible by 17. Okay. Next one. The language of all the strings that are not, their length is not divisible by 17. Well, let's think about it. L5 is, of course, contained in 0 star, right? In fact, you can think about it, L5 as being defined over the alphabet, which is only 0. It's not a very interesting alphabet, but it's a valid alphabet. Okay, now we already know that the language of all the strings that their length is divisible by 17 is regular. This is just the previous language, right? L4. So L5, in fact, is no more than 0. Well, in our case, this would be sigma, right? Sigma star, we subtract L4 from it, right? Or if you want, L5 is just the complement of L4. And this is regular, right? Because regular languages, by definition, are closed under complement, right? So this language is regular. Okay, next one. All the strings over zeros that such that the length is divisible by 2, 3, or 5. Well, let's write down all the strings that their length is divisible by 2. Well, we already know it's regular because we did similar stuff above. Take all the strings that their length is divisible by 3, and take all the strings that their length is divisible by 5. And then just take the union, right? We know that a finite union of regular languages is regular languages. Each one of those languages is regular. So this is regular, and as such, this language is regular. Oops. Okay, next one. This is similar. We want all the strings that are divisible by 2, 3, and 5 instead of all. So what we really need here is the fact that if we have two regular languages, if A and B are regular languages, then the intersection is also regular, right? Because I want to show that regular languages are closed under intersection. And this is not hard to show if you remember the De Morgan formula, right? The De Morgan formula says that the intersection of two languages is the complement of the union of the complement languages, right? So this is one of those things that is easier to see if you draw them. Right, so we have A, and we have B. Right. Now let's take the complement of B is all the red area outside. Right. And similarly, the complement A is all the area outside A. Right? So the union is going to be everything except for this little length here in the middle, this area here, right? So the union is everything except for the purple area, and as such, when I take the complement, I will get this purple area, which is indeed the intersection of A and B. So this is this, if you want, visual proof of the Morgan formula. Okay, so this implies that since regular languages are closed under complement, as we already said, and they're closed under union, it follows that they're closed under intersection. Namely, the intersection of two regular languages is a regular language, which gives us what we want here. Okay, next one. All the strings, this is the language of all the strings such that the length is divisible by 2 and 3, but not 5. Well, so divisible by 2 is regular, divisible by 3 is regular, so the intersection is regular. And now we want to subtract the language of all string divisible by 5, right? So the intersection of the two first languages we know is regular. And now I'm subtracting one regular language from another, right? So all I need to remember is that subtracting sets is equivalent to intersection with the complement, right? So this is equivalent to L divided by 2, L intersection divided by 3, intersection with the complement of L divided by 5, right? But complement, right? So now we are good to go, right? Because the complement of all the string divisible by 5 is, of course, regular, closure under the complement. And now the rest is just intersection of regular languages, which is regular, which implies that this language is indeed regular. Okay, next one. Okay, 0 to the I, 1 of the I is divisible by 2, 3, but not 5. Okay, so is this regular? So the answer is no, it's not regular, false. And at that point in time, you don't really have any way to prove it, so you just have to go with your gut feeling. But the intuition is that regular languages are all the languages that can be recognized if all you're allowed to do is to use a small counter, right? A counter that uses a fixed number of bits. You're not allowed to have a counter that is unbounded. And for this language, clearly, we need to, we need a counter that really counts the number of zeros, right? Because we require here that the number of zeros and 1 is the same, right? Which is a very strong constraint. So that's the intuition of what's going on. Of course, this is a sublanguage of 0 to the I, 1 to the I for any I, right? Which is also not regular, right? So at this point in time, the way to think about it is you need a counter to implement this language, and this counter is can go arbitrarily high, and as such, this language is not regular. But this is the intuition, it's not the proof. We will revisit the issue of how to recognize non-regular languages later on in the class. Okay, so the answer here is false. Okay, the last one is a bit tedious. So all the string over 0, 1 that contain at most 374 ones, right? So the idea is that let's look on the basic language, right? The basic language, words that are in this language. One kind of strings are all the strings that have no zeros, no one, sorry. So this is 0 star. So this is okay. Now, if I have 0 star, right, think about concatenating it with the language which either contain the empty string or 1, right? So I now get a run of zeros, and then I can concatenate either epsilon or 1. So those are all the strings that have either no ones or there is one in the end. And now I concatenate it again with 0 star. The language, the clean star of 0. So this language is all the strings that have exactly one in them, right? And now the intuition is that all you need to do to get the language that we want is to concatenate it with itself 374 times, right? Because we're counting the number of ones. In fact, one has to be a bit more, so to see why it's true, notice that we are concatenating with 374 times, but we are not forcing the 1 to appear. So if you have a string that have fewer ones, of course you can generate it. And in particular, the language written inside the outer parenthesis contain the empty string. So in particular, you can get, a string which has only 1 0 in it in the language. So this is indeed a way to generate the string. Now, this whole shebang is hinting for what's coming up, which is that there are ways to, we need more efficient ways to write things with regular languages, which are regular expressions, which are the next topic to be discussed. Thank you.